The second part of Unit 6 is gravitation, which really is just a subtopic of circular motion. So Newton's law of universal gravitation states that all objects in the universe are gravitationally attracted to each other. So that means anything, any two masses, anything that has a mass that are separated by distance have a gravitational force between them. So the equation for that is G m1 m2 over r squared. G is Newton's gravitational constant, which is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. M's are the two masses, and then R is their separation distance. So it's not like a radius of a circle. It's not half the distance, but it's the full distance between two masses from center to center, center of mass to center of mass. In example 1, we're dealing with the moon, which has a mass, and it revolves around Earth, which also has a mass. The approximate distance between the two is 3.84 times 10 to the 8th meters. What is the force between the bodies? So again, looking at the gravitational force between the two, gmm over r squared, we have g, 6.67 times 10 to the negative 11. We got the two masses. The moon is 7.35 times 10 to the 22nd kilograms. Earth, 5.97 times 10 to the 24th kilograms, and then divided by their distance, separation distance, 3.84 times 10 to the 8th meters squared. And when we solve for that, we see that that comes out to be 1.98 times 10 to the 20th newtons. Now, that's a huge, huge force, but we are dealing with planetary objects, so it's going to be a big force. That is the reason why the moon stays in orbit around the Earth. This is also the reason why the Earth stays in orbit around the Sun. Example 2 is a little bit different in terms of the objects we're dealing with, but really it's still Newton's law of universal gravitation. So we have Jack and Jill sitting 4.2 meters away from each other in physics class. Jack has a mass of 70 kilograms and Jill has a mass of 50 kilograms. What is the attractive force between them? So same thing, we got G, which is a constant, always 6.67 times 10 to the negative 11. We got Jack's mass, we got Jill's mass, and then divided by their separation distance, 4.2 meters, and we square that. So we get an answer of 1.3 times 10 to the negative 8 newtons. Now that negative 8 represents a very, very small number, so clearly the two in physics class do not have a very, very strong gravitational attraction between them. When planetary objects orbit each other, they generally travel in an elliptical pattern. Oftentimes, we will simplify this and answer questions about velocity, orbital circumference, etc. by saying the motion is circular. So basically here we have example 3, mass m circularly orbits around mass 4m at a distance of 3r. How fast must mass m travel to stay in circular orbit around 4m? So this is a good example of how gravitation is a type of centripetal force. So the reason why this mass m is able to stay in orbit around the 4m is because of that gravitational force, specifically that centripetal force that keeps it in orbit. So we have Fg, g 4m times m divided by their separation distance, 3r squared. And the centripetal force is mv squared over r, if you recall. So now that m, the centripetal force equation, is just m, not 4m, because when we talk about things going in orbit, we don't really care what's the center of the orbit. It's the mass m, that is going around in orbit in circular motion. So that's why we have m on the right side. So a few things cancel out. One of the 3 r's from the left cancels out with the 3r on the right. The two m's cancel out, and ultimately we're left with a velocity of 2 times the square root of gm over 3r. Where is the gravitational force largest? Where would you, in other words, where would you weigh the most? Is it far away from Earth, at sea level, or close to the Earth? So the answer actually comes out to be at sea level. So when you get far away from Earth, so if you're up in like the mountains or in a plane above the Earth's surface or something, because that radius is large, that means that the gravitational force is going to be small, so you're not going to weigh as much. That gravitational force on you isn't going to be as large. Similarly, if you dig deep into the Earth, you're actually going to weigh less into the Earth as well, because there's not as much mass below you. So even though you're closer to the center of the Earth, in other words, the radius is smaller, there's mass really kind of above you at that point, which doesn't really matter. So it turns out at sea level you would weigh the most. And if you want to see this firsthand with an iPad app, go to the Apple Store and search weight and mass. Download the first app. It's called Explorements, and when you open the app, click on Activities and play around with Activity 2 and 3 to answer that question. But it's a fun activity to kind of visualize. Next, we're dealing with gravitational potential energy. So we've already talked about potential energy as mgh, but that's not always completely true. It kind of depends on the situation. So as we already know, any object near the surface of Earth has a potential energy, mgh, where we define to 0 to be where we want it to be. However, when looking through a more macroscopic lens, like a satellite orbiting a planet like Earth, we use a different equation, and the reason for that is when we talk about something being far away from Earth, that's not necessarily true. That mgh doesn't really hold true anymore, because the gravitational field is not constant as we get further and further and further away from Earth. So really the gravitational potential energy is negative gm1 m2 over r. And again, just like gravitational force, r is the distance from the center of the planet. So we have an example here. The Rosetta orbiter that targeted comet 67P/CG had a launch mass of 3,000 kilograms. If Earth has a mass of 5.97 times 10 to the 24th kilogram and a distance from the satellite, and Earth was approximately 4.4 times 10 to the 11th meters on November 13, 2014, what was the gravitational potential energy between the two? So similarly, we plug in our values, or G, make sure it's negative, in front the two masses, and then just the radius, not the radius squared, and we see that's negative 2.7 times 10 to the 6th joules, which is a lot of energy, but again, we're dealing with planetary-sized objects traveling at very large speeds. Now, the last part of this note talks about escape velocity, and that's not a huge topic in this course, but still something worth knowing. So every planetary body in the universe has its own escape velocity. So this is the minimum speed required to launch an object such that it does not come down. So it actually turns out that it doesn't matter how fast we throw an object and in what direction, as long as we throw an object at a specific velocity. For example, here on Earth, there is a specific speed that if we throw it at, it will escape Earth's orbit and it will not come down. So here's just a derivation for the escape velocity. So it turns out it's the square root of 2 times g divided by the mass of Earth divided by the times the mass of Earth divided by the radius of Earth. So that's the derivation of the equation. And then we look at an example of a ball being launched straight up from Earth's surface. Earth has a radius of 6.37 million meters and a mass of 5.97 times 10 to the 24th kilograms. What is the initial speed that is required for the ball to never come back down? So we plug in the values that we know were initially on Earth. We know the radius, we know the mass, we know g obviously. So it turns out the escape velocity of Earth, any objects on Earth, is just a little bit over 11,000 meters per second, or about 11.2 kilometers per second, which actually equates to about 7 miles per second, which is extremely fast. So if we took an object like a baseball and we threw it straight up into the air at 7 miles per second, which is almost physically impossible to do, but if we can do it on our own, with our own arm, for example, we would actually see that it never comes back down, because it would be enough to escape Earth's orbit and travel into deep space.